Andersen. He will start the session with his talk. And please, Jens, you can share your screen. Okay, I guess now. Okay, and full screen mode.
Can you see it now?
Yeah, we can see it now, but it's not first probably a slide.
That is true. It's this. See? Oops, there we go.
Okay, so yeah, please, Jens, you can start.
Okay, thank you very much. Well, first of all, I'd like to thank the organizers for organizing this workshop in these difficult times. They put together a very nice program the whole week. So I've enjoyed it immensely so far. What I'm going to talk about today is, as mentioned, find isospin, and that'll be applying Chiral perturbation theory to the problem of pion condensation. And I've at the bottom of this page, I've listed my collaborators as well as a few references if one is interested in details. So you have all seen this phase diagram or similar versions of it. This is in the mu B T-plane, and there is this question mark in the middle of it. I think that's fair to put it there, since it's really not that certain the type of phases we have in that part of the phase diagram. We only have, in fact, a few results that you could consider exact, in the sense that they are really sort of rigorous results. There's at asymptotically high temperature, you have the quark-gluon plasma phase. At asymptotically large densities, you have the color flavor locked phase as well. But then in between these two extremes, you have lots of phases, but the problem is that many of those results are model dependent. So we have very sort of few rigorous results. And of course, part of the problem is that this part of the phase diagram is not accessible to lattice simulations. However, in this phase diagram, you can, if you wish, add more axes to it. We heard Monday evening there was a session on external magnetic fields. That's one way of adding complexity to the phase diagram. You can also, instead of just having one common chemical potential for all the quarks, you have one for each flavor, and that's what makes it more complicated, but also more interesting. So just to remind you, if you look at the partition function and integrate over the fermions, which you can do because the Lagrangian is bilinear in the fields, then you get a determinant, and that determinant depends upon the different chemical potentials. And unless you have particular combinations of these chemical potentials, then it's not manifestly real, and then you have problems with using the standard lattice techniques to evaluate the partition function. However, if you look at two flavor QCD and have one particular combination, namely that you have zero baryon chemical potential, meaning that the chemical potential of U quark is equal to minus the chemical potential of D quark, then in fact these complex stuff cancels in the determinant, and you have a real determinant, so you can carry out lattice simulations. And that will be the topic of my talk. Namely, I'm going to look at pion condensation for 2 and 3 flavor Chiral perturbation theory. I'm briefly going to mention kaon condensation also at T equals 0, and of course I have to use 3 flavor QCD. I'm not going to talk about finite temperature. I understand that will be covered in other talks later in the session. So let me just show you a sketch of what you expect for the phase diagram in the mu I T plane. You have the usual hadronic phase for low T and low mu I. And then if you walk along the mu I axis at T equals 0, then once the isospin chemical potential reaches the pion mass, you will have onset of Bose-Einstein condensation. Then you will form a condensate of charged pions. And the blue line then shows the phase boundary of this phase. Now, there is also this dashed red line in the phase diagram, and there might be a crossover to BCS phase. I'm not sure of exactly where that line goes, but I also understand that that's going to be a topic, certainly for the discussion later today. But I'm going to confine myself to the mu I axis, so I'm just going to, for two fibers, I'm just going to go along this axis and not into the mu IT plane. So to set the stage, just remind you, current perturbation theory, that's a low energy theory for QCD, and they're based on symmetries and degrees of freedom only. And it's systematic derivative expansion, so in principle, if certain criteria are satisfied, then this is a systematic approach where you can systematically improve on your results. Two flavors, the degrees of freedom are the pions. For three flavors, we have to add the kaons and the eta as well. Now, let's take a look at the Lagrange into leading order. There's the the kinetic term, this guy, and then you have a term that involves the quark masses, and you also have to, in the case of a chemical potential, you have to use the covariant derivative instead of partial derivative, and as usual, the chemical potential shows up as the zeroth component of the gauge field. In this case, it looks like this. There are a couple of things that I would like to point out in this transparency, namely that I've indicated that f pi, which is the pion decay constant, that can essentially be identified with the prefactor f here, and then the factor 2 b naught m, that's essentially the pion mass. It's a tree-level pion mass. But we're going to see that these receive radiative corrections, and they are actually essential to keep track of. So you can think of pion condensation, at least at tree level, as you want to rotate, or that corresponds to rotating the ground state. So here's an ansatz for the ground state put forward almost 2 decades ago by Son and Stefanov. So it looks like this. This is the sort of the standard ground state containing a quark antiquark condensate, card one, but then you allow for a pion condensate as well, and it's the angle alpha that, at least at the at tree level, can be considered or interpreted as a rotation angle. So if you now plug this ansatz into your Lagrangian and then plug out the static Hamiltonian at tree level, you're going to get two terms. And that's sort of the where the physics lies. You have this term, which is the sort of standard term coming from the quark masses. That term really wants alpha to be 0, so that sort of resists rotation of your condensate. On the other hand, you have the term involving the chemical potential mu I. That's a term that prefers alpha equals pi divided by 2. And then the two terms, they compete for a given value mu I, and then it's going to find its ground state at some value of alpha. That value of alpha is easy to figure out, and I've just showed the two possible solutions. So for mu I, starting from 0 all the way up to the pion mass, alpha is 0, and then otherwise it's cosine of alpha is given by this equation. One thing to note is that the vacuum phase that extends all the way up to mu I equals m pi is such that all quantities are independent of mu I. That property is called the silver blaze property. So it's not just that the vacuum is a single point in this along this line, it's really an interval. I'll come back to the silver blaze property for when I look at the phase diagram of 3 flavors. Then I would like to discuss a few details, namely what happens if we want to go beyond tree level and include fluctuations. You can do this in an IE way. You just use the standard representation of your U, which is this exponential involving the phi A, which are the pion fields, and then you multiply that by the rotating ground state. If you would do that, then you're going to run into a couple of problems. Once you expand your Lagrangian into, let's say, a quadratic order, if you want to look at dispersion relations. Now, the 2 problems that we discovered is that you're going to get a non-canonical kinetic term. That might not be problematic because you can think of redefining your fields. But the disastrous problem that occurs is that if you want to try to normalize your theory, you cannot do that by using the standard counter terms that you get from chi-pt. And I think one way of understanding this is that if you look, well, at least an example where you can visualize this, if you think of a spin system, then you look at this huge blue arrow that is the ground state of your system, and then you're looking at fluctuations around that ground state. Now, if you would rotate that ground state for some reason, then your parameterization of the fluctuations can no longer be correct. So you have to rotate the generators of the fluctuations as well. So you sort of parameterize your fluctuations around your new ground state. And that's, well, there's some technicalities involved in this, but the bottom line is that you have to think carefully of how you parameterize your Goldstein fields, and you have to add this operator A alpha, which is basically involves the rotation or correspond to the rotation of the ground state. This sort of subtlety was first pointed out by Splitter, Son, and Stefanov also almost 20 years ago. So then you can turn the crank and expand your Lagrangian, a bunch of terms. They're not all very interesting for our purposes right now. I'll just point out a couple of things. You can see that most of the terms, they depend upon the angle alpha. And we are just going to go to quadratic order, and you can read off the effective masses in front of the quadratic terms. One nice consistency check is that if you look at the static term and you extremise it, well, then that exactly corresponds to the vanishing of the linear term in the second line. So then at least you can see the consistency of the calculation at tree level. Okay, so we want to do an extra linear order calculation. So that involves the standard contribution from the one loop functional determinant. And then you also will have a contribution from the next to leading order Lagrangian in the static limit, or the static part of it. This was a Lagrangian that was written down in the mid-80s. There are many more terms that I've shown. Those are the terms that are relevant for the present calculation. Now, the static part involves a couple of, or 4 actually, low energy constants, and those constants, they have been determined experimentally. So that's the input we need to predict or make predictions. Then effective potential, the one loop term is given by the usual 3-dimensional integral of the energies. And another technicality is that we have to subtract and add divergent terms so we can isolate the divergences. So despite the fact that this theory is so-called non-renormalizable, we can there are no problems using dimensional regularization. The divergent terms, they go like this. The interesting thing is that they are the same form as the counter terms are. So that tells you that, at least there's hope that you can renormalize the theory. And that is actually being carried out by normalizing the parameters, as you can see in this middle line here. And I'd like to point out that this renormalization can be carried out for all values of alpha. So that means that you can get a finite renormalized effective potential that are written down here, VF. It involves the pion mass, the chemical potential, the angle alpha, and then, of course, a bunch of low energy constants, L1 through L4. And it's perfectly finite, and you can now think of extremizing this with respect to alpha, if you want to find the ground state. So once you've done that, well, let me just return to the actual calculation in a second, and then as a quick digression, just to mention three flavor KPT first. So you can play the same game. You can add a chemical potential mu s. You can make ansätze for the rotation of the ground state, depending on where you are in the mu I mu s plane, depending on the quark content of your mesons. So here are some specific examples for ansätze for the rotated ground state. Returning to the two-flavor case, we have the experimental input of the low energy constants, L1 through L4. They come with uncertainties, of course. Then we also have the physical masses. And you need to determine or express the constants F and 2bm in your Lagrangian in terms of the physical F pi and m pi. And since we want to compare with lattice results, then we use the lattice results of Androdi and collaborators. And Bastian, he will present in detail those lattice calculations in his talk. Then you get some values of the parameters, and I just want to point out that these are, of course, not exactly equal to the pion mass, the physical pion mass and the physical F pi. So this gives you the idea of renormalization or the radiative corrections that are involved in this type of calculation. But this matching is really essential, and I'll return to that issue shortly. Okay, you can, as I mentioned, minimize your effective potential with respect to alpha as a function of mu I. Here I showed the leading order result. That's a tree level result on top of the NLO result. And as you can see, these two curves are almost on top of each other. So that's not where the huge differences are going to be. The huge differences are in the correction to the effective potential itself. Now, if you want to carry out an expansion around alpha equals 0, that means around the phase transition point, then you can do that by Landau-Ginzburg type expansion. You expand your effective potential around alpha equals 0, and then let's say you go to fourth order in alpha. Then you get a coefficient in front of the alpha squared term, and it turns out that that's vanishing exactly when mu I is equal to the physical value of m pi. Now, to show this result, you really have to take into account the relation between m pi and m, etc. So if you do the calculation properly, then you see that the transition is really taking place on the pion mass. And that is a result you expect to be valid to all orders in perturbation theory. But here we have explicitly shown that if you do it carefully, then you get the transition exactly the way you expect it. Okay, results, effective potential. In this case, again, briefly, the result for the free flavor case, you have several phases here, and they compete. And then you get this nice figure here in the middle showing the normal phase. And then you have, depending on the values of the chemical potential, a pion condensed phase or a kaon condensed phase of various types, depending on where you are in this plane. The silver blaze property is still there. In normal phase, everything is independent of the chemical potentials. The transition from the normal phase to the condensed phases, that's always a second order transition. So they are solid lines. But then it turns out that the transition from, let's say, a pi plus condensate to a K plus condensate, that happens to be first order. And so are all the other transition between various condensates. They're always first order. Now this figure in the middle, or this the black line, that stays fixed, even if you include quantum corrections, because they always take place at the say the pion mass and the kaon mass. But the first order transitions, they receive quantum corrections. So the red curves, they are the tree level results for the transition, and then the green ones are if you include the one loop corrections. So there's a small change in the phase diagram, not quantitatively, but qualitatively. Let me just return then to the two flavor results. We have a number of quantities that we can compare with the lattice. I understand that Bastian, he will return to his, certainly to the equation of state in particular during his talk. So let me focus on, let's say, this plot here, which shows you the isospin density as a function of mu I. The diamonds, or the black squares, they are the lattice results from our lattice friends. And then on top of that, you have the leading order results, which is the red curve. And then you have the blue band, which is the NLO result. And the band is obtained by including uncertainties in the coupling constants, in the low energy constants, as well as in the pion masses. But here it has to be said that the dominant source of uncertainty is in a low energy constants. Okay, that is for various thermodynamic quantities, pressure, equation of state, etc. I see now that time is running, so let me just show you one more curve, or a few more curves. If you're interested in condensates, quark and pion condensates, then we have to add a source, which you can put on in this way. The source, of course, breaks the symmetry explicitly, and therefore you have not a strict phase transition, as you can see here. This is the curve for 0J, but you have smooth crossovers. And then you can look at the pion condensate and the quark condensate as well, as a function of the source. And that is very convenient, because that's what the lattice people have provide us with. So here you can see the results for the, or expressions for the condensate at tree level, and they are both multiplied by, well, this is the vacuum contribution, and then you have cosine and sine for the two condensates, so then you can really think of this as a rotation in isospin space. But if you would look at beyond true level results, well, first of all, we define some condensate deviations here, and then you can plot those deviations as a function of mu I, and then compare with the lattice. Again, the red curves are leading order results, and the blue curves are next to leading order results, and the black dots are the lattice results.
Okay, yes, could you start to wrap up? Sorry.
Yeah, I'm wrapping up in a second. The most important message here is simply that you don't see this rotation is leveling off beyond leading order. You don't see it on the lattice, and you don't see it in chi-pt. So in that sense, I think the NLO calculation is a significant improvement over the tree level results. And then I'll skip that. I'll just come to my conclusions then. And some outlook. First precision test of chi-pt next to leading order. Good agreement in general with lattice results at t equals 0. We're still working on our three flavor results. They will be out soon. For a couple of further applications, then we'll later today hear a talk about pions in magnetic field by my collaborator Prabal. And then, of course, you can also think about quantum corrections to vortices. So there are many things to work on in the future. Thank you for your attention.
All right, thank you, Jens. Right, so I'm taking over in this session, and yeah, please be reminded that right now we only want to have questions that are really short and related to the talk. Sorry. And I would also like to remind you that, sorry, could I please, or someone is unmuted, could you mute yourself first?
I think Petrov is unmuted.
Yeah, I'm not sure whether he wants to ask a question or not, but anyhow, let me first, say a few words. So please, if you want to ask a question, please raise a hand, finding that in the participants button. So please raise a hand so that I can call you. And as I said, just very questions directly related to the talk right now, and please keep the rest for the discussion, and you can also write questions in the chat. All right, so are there questions? All right. There is one by Ricardo Farias. So please.
Thanks for the nice talk, Jens. I have just a question about the values used for μi. There are some experimental expectative for the values that we will reach in experiment to compare with models. For example, on the lattice we have these values, but I'm trying to see if you have some estimatives for the large μi that you can reach to compare with effective models.
Maybe that's a better question for Bastian regarding what we can do on the lattice.
Well, so if the question is what we can do on the lattice, then we are basically bound by the lattice spacing. So that's something that I can directly tell you. So if we go to larger and larger μi, well, then at some point, basically the value of μi becomes as large as our lattice spacing, as the inverse lattice spacing, I have to say. And then, of course, on the lattice, we run into trouble. Then we're getting cutoff effects, and that's definitely not what we want. So basically, the finer the lattice spacing, the better it is for us, but then it's also becoming more difficult. So, well, I would say currently on our finest lattice spacings, we can probably go up to, well, 400, 500 MeV. But that's it, only on the finest lattice spacing. On the ones that we are typically using, it's like more like 300, 400 MeV. Okay?
Okay, but from the experimental point of view, we do not have any estimative for the high value of μi that we can reach.
No.
Okay, we have the lattice direction only until now. Okay, thanks, Jens.
All right, yeah, thank you for your question. Unfortunately, then, yeah, there is another question. It is a very short question because we want to be on time now, because the discussion, after discussion soon, there is the next question. So if it is a very short question, and Veronica Dexheimer, please. Go ahead.
Oh, it's not a question, it's just more like a comment to Ricardo's question. So if you're talking about heavy ion collisions at very small mu b, Ricardo, close to 0, those are the very relativistic ones. And therefore, those are the ones that the isospin fraction will be very close to 0.5. And therefore, the mu I will be very small. So I'm talking about tens of MeV, not hundreds. Because those things kind of go together to increase, as far as I understand, I'm not an experimentalist, of course, to increase the mu b, you lower, or the rho b, you're lowering the energy. And that's when you're allowing more isospin, the isospin asymmetry of the nuclei to show up. And then you're going to increase your mu I too. I mean, it's negative, but increases in order of magnitude.
Mm-hmm. All right, thanks. Let's keep the comment maybe here, and you can say some more. There is some more to that in the discussions later on.